Thanks, Rebecca. So this talk is about a dynamic tracing system called Fay, which we can use to instrument entire clusters of machines all the way down to the operating system kernel. And I worked on this system as part of my internship at Microsoft Research in Silicon Valley, together with Ulfar Erlingsson, who's now working at Google, and Marcus Peinado from the Extreme Computing Group in Redmond, as well as Mihai from Microsoft Research in Silicon Valley. So let's start this talk by asking a couple of questions. Wouldn't it be nice if we could just know what our clusters are doing, like where are all these CPU cycles going and where is all that memory allocated? And wouldn't it be nice if we could ask any question easily using just one simple to use system instead of having to string together a whole slew of different specialized tracing tools? Finally, wouldn't it be nice if we could collect the answers to our questions with extreme efficiency, in fact, so efficiently that we could just go and ask the questions continuously? Well, Fay is a system that was designed exactly for this purpose. And in order to give an example and demonstrate the power of our approach, let's stretch the envelope a little bit and imagine a really unusual tracing question. Let's try and apply data mining techniques to cluster tracing. In data mining, there is this technique called Backofwords that they use to classify documents without having any further knowledge about the structure of these documents. And the way that they do this is by computing n-dimensional vectors over some features of these documents, and then they apply a technique called Kmeans clustering, which we've heard about in a talk yesterday, to group documents together by vector similarity. And as it turns out, we can actually apply this technique to clusters. And the way we are doing this is we're trying to use this technique to automatically categorize the behavior of our cluster based solely on some simple metric like system call activity. And in this case, we, in order to do this, we quantize time into second-long time slices, and then we count the system calls that happen within these time slices in order to produce our feature vectors, which we can then feed into the K-means clustering algorithm. And if we do that, we get an output like this, where on the x-axis you see time, and on the y-axis you see our machines in the cluster. And then on the top we have the clusters that were generated by the K-means clustering. In this case, we asked them to generate 5 clusters. Now, of course, originally it puts the system calls into these clusters, and so we have to look at them in order to figure out what kind of cluster this is. So for the red one, for example, there were all the system calls in it that had to do with I/O. So this is the I/O cluster. And in the gray one, there was just very little system call activity at all. So this is the idle cluster. And then there are more like the memory and CPU-bound clusters. And then we can plot those over time. And that gives us a very nice overview of what is going on inside our cluster. So in this case, we can maybe already see that this resembles kind of a MapReduce workload, which we were actually running on this cluster. So on the left side, you have kind of the map phase, and on the right side, you have the reduce phase. And then the clusters quite nicely tell you what the workload was doing. So at the very beginning, you see that it was actually I/O bound. It was fetching all the data, and then it did a whole lot of processing in the map phase. And then on the reduce side, it was again doing some I/O and then some memory-intensive operations. And if you were somebody to performance debug a MapReduce workload, then this is exactly what you would want. Now, the nice thing also about this approach is that it does not just apply to MapReduce workloads. You could use this for any kind of workload that is running on your cluster. So we have actually implemented this technique on Fay and ran it on the cluster, and we got some really nice results. Not only were we able to implement this, including the whole K-means clustering in just a few lines of code, also did we run this and we did not measure any overhead to the traced MapReduce workload at all while we were trying to trace it. Finally, I should stress that there is no kind of special support for data mining in Fay. Fay is a general system for tracing. So on the next slide, I'm going to show you just the whole program that we had to write in order to show you how concise it is. So don't try to read too much on this slide. I'm actually going to zoom in on some of these things. I'm just going to say now that the top part here is responsible for grouping the system calls and producing the vectors, and the bottom part is responsible for doing the K-means clustering. So let's zoom in onto the top part to just give you a little bit of a hunch of what it feels like to write a Fay trace query. So this query language is actually a subset of the LINQ query language and a little bit of C#. So this is not a language that we invented. This is all stuff that existed previously. So on the second line here, we're specifying what to trace and essentially also on what machines. That's the cluster object there. So this says trace all the system calls inside the kernel. And then we have this where clause there that tells the system for how long to trace. So we're limiting it by now plus 3 minutes. So it's for 3-minute trace. And then we're filtering and aggregating the data already a little bit in this select class where we take the cycles, the timestamp in cycles of each system call that happened and divide it by the amount of cycles per second. That's the CPS variable up there. And then finally we use a group by to kind of generate a histogram of the system calls that happened within a time slice interval. Now, of course, we could have written a specialized tool to do all of this. And in fact, one of these tools already exists. Hakeem has been able to do probabilistic tracing like in the chopstick system. Now, I'm just listing these here to give you an overview of how general Fay is. We have details about our experience with all these implementations in the paper. Now, the key takeaways for this talk are that Fay is a system for the flexible monitoring of distributed executions that can be applied to existing live Windows servers without any modification to these servers at all. And what sets Fay apart from other such systems is a combination of 3 unique techniques. The first one is that we allow you to write a single query that specifies both what to trace as well as how to process the generated trace logs for later analysis. And that makes these queries both easier to write, as we have hopefully seen on the previous slide, as well as enabling a number of automatic optimizations that Fay can apply to these queries, as we will see later throughout this talk. Secondly, Fay is pervasively data parallel. It applies the same computation model both within machines as well as across entire clusters, which makes the system very, very scalable. And thirdly, Fay leverages the inline and safe execution of arbitrary machine code right at the trace point. So this allows us to do any kind of computation right at where the data source is. And we'll see later how that is very useful for the system as well. Okay, so let's just get back to the Kmeans query and see how Fay actually deploys this query and how it views the query on the cluster, and it then optimizes it. So this is our cluster. We have 5 machines in it. On the left side, we have 2 machines that we're trying to instrument, and on the right side, the one with the flip chart is the machine where we want to have the data ultimately in order to visualize it. And so Fay takes this query and views it as a distributed computation over this cluster. So it can use the entire cluster also to run the analysis. And then it can apply some optimization techniques that are already done in data parallel computation. So it can figure out that we're going to use the system call logs to reduce them and put them into vectors so that we can feed them later on into the Kmeans aggregation. So Fay knows this because it knows the entire query. And so it figures out that it can put the system call aggregation and the vector production right into those machines where the tracing is happening in the first place. So it can reduce the amount of data that it has to send through the cluster. Secondly, it can then build an efficient data parallel execution plan for the quite heavyweight Kmeans analysis, which could take quite a long time if there's a lot of data. So then it just starts the execution of that on the left side where the data is, and generates this data parallel plan to process the incoming logs with Kmeans using the entire cluster. So the data gets reduced as it moves from the left to the right to the machine where we're actually trying to display it. So this is data parallel computation in effect. That idea applies then also to the inside of the machines, where again Fay can figure out that since it's instrumenting kernels to count the system calls, it can just move the production of these vectors right into the kernels in order to reduce the data flow between kernels and user space and reduce the amount of transitions that we have to do between kernel and user space. That's a technique that's pretty similar to what other tracing systems like dtrace already do in order to have very low overhead when we are tracing. And then again, we have the same kind of data parallelism inside the machine. Fay can figure out that it can trace, that it can count the system calls core locally per kernel thread, and then only aggregate at some later stage, like say in user space in the machine where we have a little bit more time, or maybe even inside the cluster if that makes more sense. So what would happen if we did not have this kind of integrated query? Well, in that case, we would only know that we are tracing system calls, and so in that case, we would pretty much just log out all the data through the cluster to some machine, or maybe a number of machines that gather that data, and that is pretty inefficient because you have a lot of log messages for all these system calls that are happening in your cluster going through the cluster. So this can easily perturb or even overload your entire cluster as you're running your trace query. And then in a later step, we would load that data again and then do the Kmeans clustering, which again is quite inefficient because these disks might not be close to where we actually want to run the Kmeans. And so this is all much more inefficient than just using Fay to just produce the query and early aggregate the data. Finally, in traditional trace processing systems, it's even worse because in most cases, even though the first step is very similar, where we're just aggregating all this data to usually a single disk, the trace processing tools that we're using are not usually very easily parallelizable, certainly not as easy as the Fay trace queries, which are data parallel programs to start with. And so usually we have to do all this heavyweight analysis on just a single machine, which can take a very long time. And also we might have to compose several scripts in order to convert between data formats and all that. Okay, so far I have covered the first 2 points that you can specify a single query in order to aggregate data early and thus reduce the amount of overhead that you have in your tracing, as well as that Fay is pervasively data parallel, so you can optimize and speed up and scale as you compute large tracing analysis. So let's talk a little bit about safety of the Fay tracing probes, because this is the technology that enables us to do the early data aggregation and the computation right at the point where the data is generated, so even in the operating system kernels. Our safety is based on software-based fault isolation, which is essentially a technique that looks at a binary first statically and tries to verify that the binary is not doing any kind of malicious well, either attacks on the system or is doing any kind of non-benign operations, and then installs some dynamic guards into the binary that can then be used for those parts that the static analysis cannot easily figure out, so that there are some guards in the system that dynamically check that the binary code is not doing anything that's not allowed. And our way of making the probe safe is based on a variant of a system called XFI, which is very suitable to our approach because it works well for inserting any kind of small probe code into any arbitrary address space and even into the kernels. And we can safely reuse existing stacks or in existing threads and run our probe code right on them, so that we don't require any kind of further resources from the system, which of course, if we would use them dynamically, we would kind of change the system and perturb it, which we don't want. So we do all of this instead of using a language interpreter like done in other tracing systems like dtrace in order to optimize and run our probing much more efficiently. So this allows the arbitrary execution and efficient execution of stateful computation right at the point where the data is generated. We have configured our variant of XFI so that the probes can pretty much not access anything except, first of all, the thread local and global state that they might have in order to do their computation. So if we're counting system calls, for example, that's where we can where we can store the counts. And then we allow them to read any address in the address space that they have been installed in safely without actually crashing anything while they're trying to do this. Of course, I/O registers are protected because if you go and do I/O, then you're kind of, again, changing the system as you're trying to trace it, which we want to prevent. So these are all the three together. Now let's look at the implementation of Fay and how Fay, first of all, how Fay is installing and executing the trace probes right within the machines. So at the beginning, Fay is deploying tracing runtime in user space on each machine that we're trying to trace, and a Fay probe module, a Fay runtime module also in the traced address spaces. So in this case, it will be the kernel. And then we send the tracing query to each one of these tracing runtimes, which take the query and do source-to-source translation from the trace query to a C program, which they then subsequently compile into a tracing probe. And then that is made safe using XFI that I've explained earlier, and installed into the address space that we're trying to trace. In this case, again, it's the kernel. And then we leverage function hotpatching in order to instrument the code paths that we're interested in. Now, function hotpatching has the upside that it's very fast. For example, we measured an overhead of 200 cycles for a dispatch of an empty tracing probe. With the potential downside that we can only do function entry and function exit tracing. Now, in practice, we actually never saw the need for anything more in any of the experiments that we did, though. Now, whenever a trace event is generated, that is dispatched to the Fay probe module, which is then, to the Fay module in the address space, to the Fay runtime module, which is then responsible to find the appropriate probe that is doing the computation and processing on that trace data. And that probe can then do early aggregation, like I've explained earlier, and once it's done, it will send up the aggregated events using another technology called ETW, which is pervasively available within Windows, to the user space tracing runtime, where the user space tracing runtime can then do further aggregation or send the data on through the cluster. Now, in more detail, the function hotpatching works in this way. We, first of all, replace the first opcode of functions with a jump to a special hotpatch area, which exists in front of every function inside Windows and inside other Microsoft products. So when a caller calls this function, we jump into the hotpatch area, and in the hotpatch area, we insert a call to the Fay instrumentation module where there's a dispatcher running, and this dispatcher is then doing a lookup for the entry probes, which are then called in sequence. After that, we call a special trampoline, which is also inserted into the address space for each function that we'd like to trace, and the trampoline is then executing the original first instruction, jumping back to where to the second instruction of the original function, executes the rest of the original function, and upon return from that function, we land back in the Fay platform module, as we have called the function, on a separate call stack, and then we can run the return probes after that, after function exit, and return from the probe dispatcher to the original caller as if nothing had happened, as if the original function had just returned. Okay, so much for the implementation. What's Fay's performance overhead and scalability? So as I said earlier already, Fay adds around 220 to 430 cycles per traced function. How big that overhead is depends a little bit on the depth of the call stack that Fay needs to unwind. So in a very deep call stack setting, we had around 430 cycles. You can see on the lower left-hand side here, which shows you the null probe overhead, again, compared to two other systems, namely dtrace and system tab, that we have about an order of magnitude lower overhead in the null probe dispatch. Then we have implemented a little benchmark to show Fay scalability within the machine. We started instrumenting all the functions that exist in the kernel using Fay, as well as trying the same thing with dtrace to compare against. And then we ran a little benchmark that was copying text files on a RAM disk. So that was pretty much executing the operating system code all the time, causing these functions to be called a lot. So this is kind of a worst-case stress test for these systems. And also in this case, we could see that Fay was around an order of magnitude faster with its overhead of about 2.8 of the original runtime of the workload than the other two tracing systems. We also tried running this with System Tab, though unfortunately due to some long-standing complications inside System Tab, that are known, the system just crashed. So system tab is not a safe tracing system, whereas dtrace and Fay are both trying to make sure that the trace system is not being modified while we're tracing. Okay, so let's look at the Fay scalability on an actual cluster. This is a different micro-benchmark that we've implemented where we are tracing memory allocations and deallocations that happen in a tight loop. And we ran this workload on a 128 node, 1024 core cluster in total. We spread the work in different configurations, starting out with one thread per cluster node that was doing these memory allocations in the tight loop. So we have 128 threads in total. And then we went up to 10,000 per machine. So this is a huge workload for this cluster. There were in total about 1,280,000 threads, all of them running at 100% CPU utilization. And we had Fay count these memory allocations, and we could see an overhead ranging from 1% to 11%. So this is a really benign overhead for this huge, huge amount of work that Fay has to do inside the cluster. So there are many things that I haven't told you about in this talk that are all in the paper. Especially, I haven't really told you how in detail Fay is doing the query plan optimizations to do the early aggregation. I also haven't told you about the different case studies of the tracing strategies that we have implemented that stem from different from different previously published tracing systems. And also, there are some examples in the paper of using Fay for performance analysis that people inside Microsoft did to analyze their systems. Fay is based on, so this is like about the implementation of Fay a little bit. Fay is based on Link as well as many Windows specifics. And that doesn't mean that you couldn't build Fay on another system. Our tracing ideals, the 3 points that I mentioned in the beginning of the talk, are also applicable to other systems. So you could build Fay on Linux by using ftrace and Hadoop, for example. Finally, one caveat that I still like to mention that applies to Fay is that there's still a slight skew towards batch processing, and that's due to the fact that we actually use Dryad to do the data parallel processing, which is a kind of a batch processing system, though there is actually work inside Microsoft in a system called Naiad, which I think is very applicable to this, and I think we'll hear about that in the next session. There was certainly a poster about this. Okay, to conclude, I've presented a system called Fay, which you can use for the flexible tracing of distributed executions. Fay is both expressive as well as efficient due to the combination of these 3 techniques. So we have unified trace queries that specify both what to trace as well as how to process that data and aggregate it. Fay, due to the pervasive data parallelism, it is very scalable as well as efficient, and again, due to the safe execution of arbitrary machine code, we can be very flexible again and very expressive there as well. Finally, while Fay is a general tracing system, it is often equally efficient as purpose-built tools. Thank you.
Hey, Meysam Yavande from Yahoo Research. You reported some numbers for the overhead, but as far as I understood, the overhead highly depends on the type of the query. So for which query?
So the numbers that I presented, you mean these two? Or?
Yeah, for example, this 2.8. For which type of query?
These are all worst case benchmarks. So, we really stress the system a lot in order to see what in the worst case the overhead of Fay would be.
So what is the worst case? You had a query in mind that would generate the worst case load on the system?
No, the way you do this is you just run, you stress a very particular component of the system a lot, and you instrument that with Fay, and then you see what the overhead is on top of that.
But, so I'm trying to understand what is a lot here. So for how often?
As much as you can. So, you know, as I said, these threads had 100%, ran at 100% CPU utilization. So they were all the time, they were in a tight loop doing this. So these are micro benchmarks. It's just the regular way you do micro benchmarking.
So do you have a benchmark that you send a query and you see how the system is slowed down by this query?
What
so
do you mean?
the overhead in the system highly depends on the query. For example, a query might need lots of the data from the system. So you will ask and you gather more data from the system, so you add more overhead to the system. And the system slows down more.
Yeah.
So do you have numbers for different type of queries, or you have very particular query in mind and you run experiments based on that?
So there are some numbers of that inside the paper. So the one example that I gave with a real query that was at the very beginning is where we had no measurable overhead. So the system is very efficient.
So as a user, should I be expert? Should I have the knowledge of the internal of the system and be careful not to write a query that adds too much overhead on the system?
No, in most cases not, because Fay will be able to figure this out automatically. I mean, there might be corner cases where it doesn't, but I wouldn't know about them. So, no.
Thanks.
Ivan Beshasnik, University of Washington. So your system bundles computation with data generation. So it presupposes that you know the question you want to ask, right? Whereas other tracing tools tend to log the data and then offer the flexibility of asking whatever you want at a later time. So I'm wondering do you have any intuition for how common this use case is in practice?
So you're talking about approaches like the flight recorder, where they are trying to do anomaly detection, and they just log data for a long time, and then whenever there's a failure or something going wrong, you can look at the
that's
data.
One application of the log data, but you can use it for any kind of analytics.
And your question is?
And my question is, you bundle computation with data, so you don't, the data that you get out is aggregated. So if you want to ask a different question about the same data, it's no longer possible. You have to compute the query and run it again.
That's true. So I think that is definitely true. I mean, if you use the knowledge that you have of what you want to use the data, then you're aggregating in a specific way and you're reducing the data there. So yes, if you later on want to use the same data set to ask a different question, then that data is gone in this case.
Thank you.
So this is more of a dynamic instrumentation system where you really want to, you want to ask a question right now at this point in time.
Martin Schwarzkopf from Cambridge. My question has just been asked, but I'm just going to follow up on this with asking, surely you could support this kind of case by having no reduction in the system, right? Or would it blow up?
Oh yes, of course. No, you could do that, of course. But then
you would
again,
generate massive
then you
amounts
run
of
into
log
the
data,
same. Then you run into the same kind of problems. I mean, that if you want to, so you can do several things. You can either you write a Fay tracing probe that does aggregation of the data or stores the data somewhere where you don't have that much overhead, and then you have the probe written in such a way that you can read it out later. That's possible because you can write arbitrary trace probes. There's nothing hindering you from just compiling a probe and putting it in so that it does such a thing. I was thinking about a case where you really wanted to just get the data immediately in the previous question. Maybe I was misunderstanding that. So this would be possible. Yes, you could also do that with Fay.
Do you have any intuition of whether it's going to blow up if you do that in a bit?
Well, you would do this. So this is kind of one thing that I mentioned in the beginning, where we also implemented a technique that is done by the flight data recorder, which is essentially a system that is storing data for a long time. And then when you have an anomaly, you can read it out later. So if you implement it in such a way, then that's possible.
Okay, thank you.
Hi, Rodrigo Fonseca from Brown.
Yeah.
So it seems that to do correlation across the entire cluster, since you can't change the flow of computation, you're essentially relying on their clocks to be synchronized. Is that how you correlate events across different nodes?
So I don't actually know the detail about how the events are correlated through the cluster. One way is definitely you could do that with clock synchronization. That's true.
Oh, that's partially true because clocks are not really synchronized. Right?
Yeah.
Or they can get out of sync.
So unfortunately, I don't know how that part of the aggregation works in detail. I'm sorry.
Okay, we can talk more.
Yeah,
thank you.
Let's take it offline.
Hi, Yan Pei Chen, UC Berkeley. First, thank you for doing this work. I think tools like Fay are really helpful for help us understand systems, how they function. I'm just curious, have you discovered any design insights or performance insights yet with Fay that you could not have discovered otherwise?
We did, yeah. So this was actually used inside Microsoft to trace some of their production systems. And I think there's one story in the paper where they were able to to use the system in order to find a performance regression. In fact, I remember one right now where we have been using Fay, just starting to use it, and we had the shell open, and we saw that the shell was actually having quite a big overhead on the CPU, just running there being idle. We traced that one, and we saw that it was doing a lot of interaction with the console server inside Windows in order to, whenever actually this was when we were typing out a file, so we were just trying to type of a file, so we were just putting it out on the console, and even when the window was minimized, there was quite a huge CPU overhead. And what happened was that there were actually two calls all the time to check whether the console was actually a real console, or compared to just being, typing it out to a file, to another file, which could also be the case because you can do redirection. And it was doing all this communication, which are remote procedure calls between these two domains, and that's where the overhead stemmed from. So this is one quick example of where we used it for analysis of a real system.
So this is a specific case where the Fay's choice of tracing system calls really allow you to identify that.
Yeah.
Okay, cool, thanks.
Okay,
So-
thanks.
Okay, thanks.
Thanks, Sami.